Okay guys, let's talk about something that we call activation energy. That's a concept that we're going to explore a lot more in the next module as well. Okay, so remember that collision theory, which was the theory that reactions occur when molecules meet, collide with enough energy to overcome electron-electron repulsion and in the correct orientation. Okay, so just a little revisor there. So if we do a graph like this, okay, on the left-hand side, where we're talking about energy on the y-axis and the progress of reaction on the x-axis, okay? And on the left, we've got the reactants, what goes into the reaction, and on the right, we've got the products, okay? We're going to think about the energy required for a reaction to occur and start to connect it with things like endothermic and exothermic, and leading into next module, okay? So here, I'm using the example of the combustion of octane. We know that the combustion of octane is exothermic, we call it as a fuel, so heat is produced through the reaction, or energy is left over on the product side, okay? Therefore, the energy of the reactants is up here, is high, and relative to the energy of the products, which is lower, okay? So the reactant started a higher energy, the reaction goes through, and the products, the energy in the products, so the energy in the chemical bonds, is less than that. So there's energy left over that's given out as heat, okay? If this is true, why doesn't a jerry can of petrol just combust spontaneously when you leave it open in the air, okay? It doesn't happen because there's this concept that we call activation energy, and we'll relate it back to collision theory as well. There's an energy barrier. So activation energy is an energy barrier. So an energy barrier will stop some reactions from occurring spontaneously, and we name this activation energy. So here on our graph, again, we've got the reactants up here and the products down here. There's a energy difference there, but we've got this energy barrier, this hump in the middle, that the energy of the reactants need to increase to jump on over to release all that energy as the products. So that is what's stopping that jerry can of petrol from combusting, okay? It's all well and good to think about it graphically, but what actually is it? We'll get to that. Let's contrast it with an endothermic reaction. An endothermic reaction, remember, cools down in the environment, so it takes energy from the environment. So its products need more energy in its bonds than what were there in the reactants. So here the reactants are same place actually as before, but the products are higher up here. And again, you still have this activation energy barrier that needs to surmount to go down to the products. Okay, so you still need some activation energy. So this one is endothermic, and this one here is exothermic. And sometimes these diagrams are called energy profiles, or might refer to them as energy diagrams. It's talking about the progress of the reaction and the changes in energy of them. They're very handy diagrams. Okay, now onto what this activation energy actually means down at molecular level. All it is a representation of collision theory. Okay, it's a representation of the energy that's needed to overcome electron-electron repulsion and the energy needed to have enough spin on the molecules so that they have the correct orientation. Okay, so to overcome the activation energy, the reactants need like a spark or an input of energy to overcome this electron-electron repulsion. Okay, and also get enough collisions that are correctly orientated. Okay, so all the activation energy is collision theory. Okay, so graphically we see that is this hump of energy that's needed. It's just collision theory. Okay, so graphically what happens when you're heating a reaction? Well, when you're heating the reaction, you're getting more molecules. Remember that Maxwell-Boltzmann curve that broadens, okay? You're getting more molecules that can meet that energy barrier or get over it, okay? So what you're doing here, when you heat your reactants, instead of being down here, you're raising them to a higher level, okay? A higher energy. The energy at the products is staying the same, and the activation energy, well, the top of it is staying the same as well. This is the energy that you need to get all the correct orientations and all the correct energies to overcome collision, overcome electron-electron repulsion. So the higher you go up, the activation energy lowers and lowers and lowers until it's zero. And then you get all of it spontaneously collapsing into its products, okay? So that's what happens with this energy profile when you heat the reaction, okay? The activation energy gets less and less and less until it disappears, okay? If you're doing something like increasing the concentration of the reactant or increasing the surface area or mixing to ensure successful collisions, what we're doing there on the how we represent that on the energy diagram is we're decreasing the activation energy. The energy of the reactants and the products are the same, but we're lowering the hump that they need to get over, okay? So increasing concentration, surface area, or mixing lowers the activation energy to become a lower value. Okay, catalysts. Okay, remember a catalyst, something that takes part in the reaction but it's not consumed. So it's kind of like a matchmaker. Graphically here on the energy diagram, they represent a new pathway that still starts at the same energy for the reactants and ends at the same energy for the products, but the activation energy is lowered, okay? So here in blue is your uncatalyzed path, or just the normal activation energy for the reaction, and add a catalyst into the mixture and it lowers, okay? A little bit extra here too. Sometimes a catalyst can introduce or cause more reactive steps in between. So what you might actually get is a catalyzed pathway that has a couple of humps in it, or 2 or 3 or something like that. But overall, the smaller activation energies are a lot less than this large one, okay? So you get a smaller energy profile or smaller energy curve when a catalyst is added. Okay, I think it looks like here I'm talking about an example. Here we've got sulfur dioxide gas and oxygen going to sulfur trioxide. And you can see on the left here, it's a homogeneous reaction. It's all happening in the gas phase, gas, gas, gas. And on the left-hand side, we've got 3 molecules, 2 of sulfur dioxide and 1 of oxygen, aiming to collide at the same time. So 3 molecules colliding at the same time is pretty rare, okay? Think about balls kind of bouncing around inside of a box in 3-dimensional space. 2 likely to hit each other, collisions between 2. Collisions between 3 in exactly the same moment are going to be pretty rare, okay? So the activation energy for this reaction is high. It's due to the amount of the reactant molecules that need to collide at the same time, okay? So here we've got 3. So you can see that it has a high activation energy. But what actually happens when this reaction is done in industry, it's catalyzed, okay? It goes via a different pathway. First, the sulfur dioxide is reacted with nitrogen dioxide to form 1 molecule of sulfur trioxide and 1 of nitrogen monoxide. Then they take that nitrogen monoxide and then they react 2 of them with oxygen and then they get 2 nitrogen monoxides, okay? And then they feed that back in. All right. So this is the same reaction, okay? If you reverse that one and add them together, you'll see that that's the same reaction. So it's just producing more. I'll do that in a second. All right. So it's the same reaction. It's just going via several different steps, kind of like what I showed in the catalyst before. So if we reverse the second one, I haven't left enough space here to work. Okay, I'm just going to draw it over the top. SO2 plus NO2 going to SO3 plus NO. If you put the NO2 down there and it... Oh, hold on. No, you don't reverse it. You just add them together. What am I doing? Okay, let's add them together. Don't worry about me. Of course you're not reversing it. We haven't got up to that yet. NO, 2 NOs, plus O2 goes to 2 NO2. Okay, to add them... Ooh, I'm going to times this one by 2. Okay, so 2 goes to 2NO, and that way I get 2NO2 cancelling out, 2SO3 and 2NO. Okay, add them together and cancel anything that appears on the both sides. Okay, so like our redox reactions. Okay, so 2NO on the left will cancel with 2NO on the right there. 2NO2 will cancel with 2NO2 there. And what do we got left on the left? 2SO2, same. 1 molecule of O2, same. And 2 molecules of SO3. So these two reactions happening at the same time and adding together equals our original reaction. We're just going via a different pathway. So it's the same reaction. So here, if we're just using our general graph energy profile here on the bottom right, our uncatalyzed pathway is hard to do. It's a large activation energy because we've got to collide 3 gaseous molecules at the same time. But if we take it this other pathway, it's just got a lower activation energy because we've got 2 and then 3 molecules. So, I mean, it's 2 reactions, so we're going to have 2 humps. But don't worry about that too much. So let's just model it like that. It's going to have lower activation energy. So this catalyzed way, we're getting to the same products, we're starting with the same reactants, but we're going in a more energetically favorable way because it's lower energy. Okay, you can watch that video on catalytic converters and how they do catalysis as well. Ooh, catalysis, I haven't talked about that word yet. That's the process. Okay, another application of catalysts is biological catalysts. So living things use catalysts to make reactions faster or happen at a lower temperature. And these are large, complex organic molecules, so they contain a lot of carbon, hydrogen, and oxygen. And they have funny shapes, and we call them enzymes. So enzymes is a biological word for large molecules that break stuff down. Okay? So they're made up of proteins, which are large molecules that are scrunched up together in a particular way. And that's what this diagram's showing you. They use, biologists use this type of diagram once molecules become so big, but they try to show shape, okay? Shape is awfully important for biological molecules like proteins and enzymes and amino acids and stuff like that. Anyway, excuse me. So enzymes act as catalysts for a reaction that will need much more energy or temperature if they were happening outside of an organism. Oh dear. Glucose and oxygen. So here we've got respiration. Glucose and oxygen come together to give carbon dioxide and water, so the opposite to photosynthesis. So we're talking about, it seems like a combustion reaction. You can combust glucose at higher temperatures. But living things that respire do that same reaction and get the same energy out of it, but without going to combustion temperatures. So they lower that. They must lower the activation energy for this reaction. And it's lowered by these enzymes. Okay? So enzymes make this combustion reaction happen at 37 degrees Celsius for humans. Okay? So they work in very small concentrations and they're like an introduction kind of catalyst. They bring things together. Okay? And they speed up reaction times by 1,000 to 100,000 times. That's a huge amount. That's crazy stuff, okay? So usually with catalysts, when we're talking about real chemistry, we might double the speed or triple the speed or something like that. But, you know, orders of 10, that's crazy. but thousands to hundreds of thousands of times. I like what I say here. Another case of billions of years of evolution doing a better job than 400 years of science. So many of these reactions that we want to happen, many scientists are looking into using enzymes to do the reactions they desire, because nature has had its 4 billion years to do a really, 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 really good job. All right, so there's an application of catalysis in living things. All right, that is all for the content for this chapter. I put that compound interest thing in as a summary. That's a nice summary of the different conditions. And there's the should know and should be able to. Thanks, guys.